Okay, so we are going to get started. Um, the slides that I sent you all was covering what linear modeling, right? So the first thing I want us to start with is just kind of do a quick little overview. Um, there were three different ways that we said you could actually represent a model. Who remembers what those three ways were?
One was graphing, right?
One was graphing, yes. One was with a graph.
Order pair or order pair.
One was ordered pairs, very good. And what was the last one?
Equation.
An equation, very good. So we had graphs, ordered pairs, or equations. Those are the three ways that we could represent linear models. So what we're going to do today for our examples, we're just going to look at a couple of different examples for those three methods of representing linear functions. First, we had specifically wanted to talk about what? Functions. And there was a very particular definition, a very particular thing, a requirement for something to be a function. Who remembers what that requirement was? So for our linear modeling, we're going to be specifically looking at
You have
functions.
to have an input and an output.
So you do need an
Only
input
one
and an
input.
output. What else is it?
It said only one. I mean, only is only what? Only one output.
You on the right track, but you're missing something there.
What
Relationship.
input?
Every input has only one output.
There you go.
Something.
Exactly.
Yeah.
There you go. So yes, it's a relationship where every input has exactly one output. That's the requirement for something to be a function. So every input has exactly, right? That exactly tells you it's not two, it's not at least one, exactly one output. And that exactly one is the critical piece right there. Exactly one, right? It basically tells us that for something to be a function, we have to know what's going to happen when we put something into the function. We have to know exactly what we're going to get out, right? It's not a function if we don't know what we're going to get out when we put something into the function. So let's look at a couple of relationships. Let's say for the first one, we have something like this. I'll do. Here are our inputs. And when I put A into the function, I get out B. When I put B into the function, I get out C. When I put C into the function, I get out D. When I put A into the function, I get out E. When I put B into the function, I get out F. And when I put C into the function, I get out G. Is this a function? Would this represent a function? Those are the inputs on that side. These are the outputs. Would this represent a
Yes,
function?
they got one output, right?
Say it again.
Yes, because it only has one output.
Does it? What input are you saying only has one output?
Like, I mean, it would get one output, not like, not two of them. Like A and B can't both equal C.
So, okay, let's look at our inputs. What do you get out if you put A in?
No, it's not.
B.
You get B and
B.
E.
B and E? No, you don't get B and E.
And B.
It's B or E. You get
B
B
or E.
or E. Which one is it? How do we know which one it is? Right? So when we put A in, we could get B or we could get E. What about when we put a B in? What if we put a B into the function if our input is B? What can we get out?
C or F?
A C or an F. And what if we put a C in our function? What can we get out?
A D or a G.
D or G.
So when you put a letter, an A or B or a C into the function,
It's not a relationship.
do you know what you're going to get out? Well, it is a relationship. It's just not a what?
It's not a function.
Exactly. It's a relationship that is not a function. A function, every input has exactly one output. So it is a relationship. It's just not a function. Right?
So it's not a function because it has different outputs. That's what you're saying.
So it's not a function because we have inputs that can give us like an either or situation. Right? So some of our inputs, right? If we put A into the function, we don't know what we're going to get out. See, because we could be here or we could be here. We don't know what we're going to get out when we put A into the function. That automatically makes it not a function because every input does not have exactly one output. Some of our inputs have more than one output, more than one thing that can come out when we look at it. Let's look at another scenario. So we'll have our inputs and our outputs. Right? What about this? If we have 1, 3. Would this be a function?
No.
Hmm?
No, it's not a function.
Does everybody agree?
Yes.
Yes, we agree because we look at it, we got the input of 1, and that's just like a toss-up. That's like gambling or something. We don't know what we're going to get out when we put a 1 into the function. We don't know what we're going to get out. All right, let's try another one. This time, I'm going to write my function. Okay, let me just rewrite it again. This time, I'm just going to write my function as an ordered pair where I have input comma output, right? I'll write it as an ordered pair and you all will look at it and see if it's a function. Don't forget, put your thing on mute if you're not speaking. So would this be a function?
Yes.
Yeah.
This would be a function. Why? We look at our inputs.
Why?
None of our inputs repeat. Right? None of them repeat. So that's good. That makes it a function because none of them repeat. Right? None of our inputs give us more than one output. All of our inputs, they all check out. 1 gives us 2, 2 gives us 3, 3 gives us 4, 4 gives us 5, 5 gives us 6. Let's do another set. What if we had this? Would this be a function?
Yes.
Yes.
So Shalea
No.
said no.
I did. I said no.
No.
I was thinking
I
the
thought it
same
would have
thing.
different outputs. It comes out with one output, right? So I thought.
Go ahead, Ashley. What you saying?
Undefined thing.
Because example in the slide
Yeah.
was like they had the same input and they both gave like one output, so even though it was the same.
So what's the solution? What are y'all saying? Function or not function?
It's a function.
It's a function.
Okay.
I don't know. I'm just gonna say no because I don't know.
Okay. Anybody else have a theory?
I thought it's input. I don't know. Hold on.
So the only thing you need to look
Do
at
it
is
have
this requirement here. Every input has exactly one output. If every input has exactly one output, it is a function.
It's a function.
So does every input have
I
exactly
feel
one output? Yes.
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 None of these inputs repeat. Yeah, they all give you the same output, but that's okay. Right? What do they say? There's more
Okay.
than one way to skin a cat? right?
Mm-hmm.
So yeah, you could do something. You could get to the 5 in a bunch of different ways, right? But each of those ways gets us to one exact output, right? And again, I just want you to imagine if this was like the world. It's kind of chaos if we don't know what's going to happen. If it's just a toss-up, we do something and it's a toss-up. We put some input into a function and it's a toss-up what's going to happen, right? That is not a good scenario. We don't want that kind of scenario. We want a world where every input has exactly one output. You do something, you know exactly what's going to happen, right? So, any of y'all Geminis? No? Yes, Shalea? So with y'all Geminis, you could get a Tuesday Gemini or a Wednesday Gemini. It's different. It's just a toss-up which side you could get when you have a Gemini. It's just a toss-up, an absolute toss-up. You don't know what you're getting, right, when you are friends with a Gemini, right? You do you agree, Shalea? Why are you not talking? Why are you just typing in the chat? Where you at?
That's not true.
That's not true?
No, that's not true.
That's not true? I think it's true.
I say that's a Libra, but okay.
See, I think this is just the Gemini side of you that's speaking. That's what I think is happening. It's just the Gemini side of you that's speaking. So, and it's definitely not a Libra thing. I'm a Libra. It's not a Libra thing.
It's a Taurus thing.
Taurus, yes. Gemini, definitely.
Excuse me, I'm offended. I'm a Taurus. I'm offended.
All right. So, this is like just that idea of recognizing functions, right? That's the basic idea. We're just recognizing whether or not something is a function. Again, the key concept, every input, right? Exactly one output. All you need to do is look at your list of inputs and see if there's an input that gives you more than one thing as an output, right? Just look at the list of inputs and see if anything is any of the inputs are repeating. Okay. So now the next thing I did want to touch on really briefly is I wanted to look at graphing, right? And I just wanted to kind of just briefly touch on the graphing thing. I feel like most of you should have had some exposure with graphing before in the past. Uh-oh. My line wasn't straight. There we go. There we go. So, on our graph, just like in the video, just like I explained in the video, this line going sideways, that is representative of our inputs, or X. And the line going up this way, those are our outputs, or Y, right? And it can go negative, positive, whatever. We're basically just matching inputs with outputs. And a point, if we pick a point represents an intersection between a certain input and a certain output. So for example, if I pick this point here, that point represents an intersection between this input right here and this output, right? And it's basically telling us that when we have a certain input, right? When we have a certain input, we're going to get this output, saying those two are paired together, they're mapped together. This input here goes with that output. So let me put some numbers on here, and we'll just do some graphing examples really quickly. Just to show, we'll graph one thing in each quadrant to go through that process. So the ones we'll graph 2, 6, we'll graph -5, 7, we'll graph -3, -8, and we'll do 6, -4. So we'll graph these points here. Each of these lines on here represents 2. So that's 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. That's -2, -4, -6, -8, -10, and then going down we have -2, -4, -6, -8, and -10. And as a bonus, I'll also graph these two. So I will graph 0, 4, and we'll graph 4, 0. So we can compare what those two look like. So starting with the first one, 2, 6. So anytime we're doing any kind of graphing, right, we always start at the origin, right? The origin is this point right here. That's home. We always start at that point in the middle, that origin point. And then what we do is we march over to the correct input and we march up to the correct output, the matching output. So for the first one, what is the input for the first one?
2.
2. So we're gonna march just over to 2, right? And then when we're at 2, what do we need to march up to?
6.
And we get right there, and that is 2, 6. Right. So that is where we needed to march up to and over to. All right. Now, let's do the next one. What are we gonna march over to? The next one is what? What's the input?
-5.
-5.
Yep, so we're
you're
gonna
go
march
to the
over
left.
to -5. And -5 would be in between -6 and -4. And then we're gonna march which way?
To the right.
Oh no, down.
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 What's
We're
the
gonna march
output?
down.
No.
Almost.
Output is up.
7.
7. So we're gonna
Oh, no,
march
it's up,
up
'cause
to
it's up.
7.
7. Up.
Oh no.
That's in between 6 and 8. So with that, we have -5, 7. Now the next one is -3, -8. So which way we marching was negative, so we're gonna march over.
Mm-hmm.
-3, and then we march down to -8. And then we have 6, -4. So we march over to 6. That's our input. And we march what? Down
Down.
to -4. Right? And then we also have 0, 4. So are we going to march anywhere for 0, 4?
No.
No, because the input is 0. We're already at 0. So what do we need to do? We just need to march up to 4. And that gives us a point right here. Right? That is 0, 4. And what about 4, 0? What's our input for 4, 0?
4.
So we need to march over to what?
0.
No, we're already at
I mean,
0.
go
We're
to the
marching
four.
over to the
Go to the
4.
0.
And are we marching up or down?
Nope, you stay on the.
Exactly.
No,
We're just going to stay right here.
You
'Cause
stay on the 4.
yep, we stay right there because the Y was 0. So we don't need to go up or down. We're already at a 0. So that is 4, 0. Four, 0. All right. So that's a little bit of graphing, just kind of looking at the idea of putting some different points in the graph. Now, one thing that I do want to point out, for us to make a line, all we need is 2 points, right? And one way you could think about it is eye contact, right? So let's say, let me pick on some people. Let's say Shamika and Aaliyah are in a room, right? And they're the only people in the room. They've been waiting there for ours, and they're moving around the room. Anywhere that those two people move around the room, can they make eye contact and make a straight line between the two of them?
Yes.
Because it doesn't matter where they are, right? If you just think about somebody, as long as you could see them, you can make eye contact and look directly at them, right? So that's the idea. Imagine that Shamika and Aaliyah are both points. Wherever they move around, they would define a line that goes from Shamika over to Aaliyah. Because and that line would basically be their eye contact. That's a straight line, the easiest way. So they could move around, you know, maybe they're getting uncomfortable, so Shamika moves to the chair on the other side of the room, and Aaliyah moves to one chair over there. They still make a line. It might be a different line if they move, but they still make a line. Right? So that's what we mean when we say we only need 2 points. So if I put 1 point here, right, I have not defined a line with just 1 point. Right? For me to define the line, I need one of two. No, there's only one other thing that I need. I need to get another point on the line if I want to draw it. Now, to get the other point on the line, either I can just get somebody could just tell me, hey, here's the point on the line, or I can use the slope, right? And the slope will let me find another point on the line, because the slope is what? What's the slope?
Intercept.
No.
It's a point on the line. 2 points on the line.
No.
What's the slope?
What did we say the slope was? There was a letter that represents the slope. What did we say the slope was?
No.
Oh,
No. The M.
Y.
Yes, it's M.
It's M.
It is M. But how do we find it? We can't hear you, Aaliyah. You on mute.
It's y equals mx plus b.
No, so the slope is the M in that equation. But how do we find the actual slope? It's 2 words. Something over something.
Rise and fall.
Oh.
Rise over run. Yes. That is the slope. The slope is the rise over the run, right? Which is basically how far up we go divided by how far over we go. And we can use the slope to find another point on the line. And once we have another point, right, that will allow us to draw a line. So let's say here I said our slope was M equals 4. Is 4 a fraction?
Yes.
Yes. What's the fraction that makes 4?
Isn't it like 4 over 1?
There you go. Exactly. So when we say that the 4 is the slope, that's basically saying really, I'll just write here, 4 over 1, which is our rise over our run. Rise over run. So what's the rise? To get from one point to another point, what's the rise?
4.
And what's the run?
1.
1. So the rise is basically how far up you go, and the run is basically how far over we go. So we can either go forward or backwards to get to the next point. Let's go backwards to get to the next point. So if we're here, right, let's say this is point 2, and we want to find another point over on it, right? To get to this point, we did a rise of 4 and a run of 1. So let's undo that. So we're going to go down 4, because to get to the other point, we went up 4. So let's go down 4. So we're at 8. We're going to go down. How far should we go down?
4. Or no?
Exactly. We should go down to 4, which is right here. So that's the rise. And now let's undo the run. What's the run?
Over 1.
1. So we need to go over 1, which would be just to right here. So we went down to 4 and we went over, and there goes our other point there using the slope. Right? So the coordinates for this point were 8, not 8, 10. I did it backwards. 10, 8. And the coordinates for this point are what? 9.
That's 9.
4. Now we can make a line, right? Now we can make a line. This is Shamika. And this is Aaliyah. And we can make a line that goes right between the two of them, right? And the reason why we say that this represents a line is because if we wanted to, we could extend this line to include the rest of the class. I know that doesn't really look like a completely straight line, but just use your imagination. It just goes on and on and on to infinity, right? That's what the line does. It goes on and on and on to infinity. Right? So we can just extend the line all the way down, and it makes a line. That's basically what a line is. A line just continues on and on. So that's the slope. Let's do some word problems. Because I know that's y'all's favorite thing, right? No? Not word problems? Y'all don't like word problems? Okay, I don't know. I just swore that was what y'all liked. I swore y'all liked word problems. Alright, so let's do a word problem example. So for the first example that we're going to do, what question you got, LaKenya?
All of them.
Yeah, but you gotta ask a question. All of it don't. That's not a question. I need a question.
Just keep going, and then I'll see.
You'll see at the end? Okay. Alright, so let's do a word problem where basically we're going to try to represent the function. So let's say, who did I pick on? I already picked on Aaliyah and Shamika. I'm going to pick on, I'll pick on Bianca. You there, Bianca? Maybe not? Okay. I'll pick on somebody else. Rashida, you there?
I'm sorry, I'm here. I thought my computer was off mute.
Oh, okay. All right, so I'm going to pick on Bianca. So,
I'm here. I'm sorry. I probably should have stayed on mute because I don't pick on me.
I'm picking on you. Yes, I'm picking on you. I already decided. So I'm picking on Bianca. So, Bianca, you like to bake, Bianca?
A little bit.
Okay, so Bianca has a bakery. And up until now, Bianca's kind of just been winging it and just doing whatever in her bakery, right? She's not really counting the numbers. She's just like, I pay some money, I buy some brownie mix and stuff. I make my brownies. I don't really care about the numbers. It seems like I'm making money. But then Bianca took Professor Salam's class. Professor Salam said, no, you need to run the numbers and you need to actually map out exactly what's going on. So Bianca says, okay, I'll do it. So Bianca realizes that when she makes, when she makes 100 brownies, the cost, right? Her cost. That's fine. We got you, Rashida. So when she makes 100 brownies,
Where it go?
so she makes 100 brownies. The cost is, what's the cost for 100 brownies? The cost is $37, right? And when she made $250 brownies for a different event, right? The cost was $52, right? And Bianca, because she understood everything in class and was like, yes, I know how to do this, Bianca assumed that the relationship was linear. That the relationship was a linear function. Right, and basically what this means is that we can use that equation I gave you for a linear model, for a linear function. We can use that equation and it's a function. So that means every input has exactly one output. So Bianca, assume the relationship was a linear function, right? Help Bianca create a model for this situation. So, first thing we need to do is what? What's the first thing we always do?
Find.
Define.
Always, without fail. It's always going to be the find. Now, it said help make a linear model, but there were a couple of different ways that we could represent a linear model. Are we going to represent it like this? Are we going to represent it like this? Are we going to represent it like this? Or are we going to do all three? What do you all think? Oh, that's a good idea, Ashley. Do all three. Thank you, Ashley. That's a great idea. So we'll do all three.
Who said that?
Ashley DeCosta.
I said one.
No, I heard you say do all three. That's what I heard you say. I heard you say do all three. Okay, Ashley. Thank you. So, what were the three? We need to make some ordered pairs. So that's our find. We're going to find at least a couple of ordered pairs, right? We need at least two to make a line. We need to make a graph. And we need to write an equation. And what form will the equation take?
F of X
Okay, go ahead.
equals what?
Equals Y, which equals what? MX
X plus B.
So Y equals MX plus B. But F of X and Y are kind of interchangeable. So we could say F of X or we could just say Y. Either one is fine, right? So F of X is the output of the function or the name of the function, or we can say Y for the name of the function. So either one is okay. All right. So we need to do all three of these. So let's start off with the ordered pairs. So let's go on our given. What information does the problem give us? So let's read through it. So Bianca has a bakery. Is that important?
No.
Not really. No, that's not really important. When she makes, I wrote when she makes 100 brownies, the cost is $37. Is that important?
Yes.
Yes.
Yes. So what does that tell us? How can we put that information into the construct of what we're understanding here? Right? How can we put that information? Maybe we need to first examine the scenario, because for any kind of function, any kind of relationship, what do we say we need? We need a what and a what?
Input and output.
We need inputs and outputs. So let's find out first what our inputs and outputs are going to be, right? And then we can say maybe one of these numbers is an input and one of these numbers is an output. So let's look at it and see. Our input will be also called our what?
Given.
Our independent variable. Why is it called our independent variable? Because we can control what it is. What do you all think is the thing Bianca can control? What can Bianca control? Can Bianca control the cost? Somebody said it already. Yes, very good. So our independent variable will be the number of brownies, because that's what Bianca can control. If Bianca doesn't want any cost, she just better not make any brownies, right? If she wants to make 1,000 brownies, the cost will be dependent on what? The number of brownies she makes. So what she controls is the number of brownies. And what do you all think the dependent variable will be?
Amount of money.
The amount of money. Let's be more specific.
The amount of money she's going to make.
She spent. The amount of money she spent.
Yes.
Is it a cost?
Oh,
the cost, right? That's going to be our dependent variable. It's going to be the cost. So yes, it's the amount of money, but it's the cost. How much money she's going to spend, pretty much. So let's come up with a variable to represent the number of brownies. We can just use X. That's okay. Sometimes you spend so much time thinking of like the right letter. You can just use X. So are y'all okay with that? Using X for the number of brownies?
Yes.
So we'll call this X, and what will we call the cost?
Y.
Just call it Y. That's usually what we do. Usually we can just call it. Sometimes, right? Like it makes more sense. Like for example, if you were doing a presentation, right? If you were doing a presentation, it makes sense to use variables that match whatever the scenario is. So maybe we'd use like N for the number of brownies and C for the cost, or something like that, right? Just like when we did those functions before. Remember we did the functions before with the financial stuff, right? And they would use letters that matched what the input was. So like one letter might be Y for the number of years, or R for the interest rate, A for the accumulated balance, PMT for the payment amount, right? So sometimes it does make sense to go ahead and use something that use a letter that actually matches the scenario. But in this case, it's okay for us to just use X and Y. All right. So now we know our independent variable and we know our dependent variable. So when we look at our given, shouldn't we be looking for stuff that goes like this? Right? For inputs and outputs that go together.
Mm-hmm.
So do we have any inputs and outputs that go together in this case? So where were we? We were in this sentence here.
And the $37.
Say that one more time. So this is the sentence we were in.
Yeah, 100 brownies is 37.
So what should we write?
100 and the 250.
Tell me what to write.
100
And the 250.
37.
and then 250, 52.
Put your things on mute when you're not talking. 250 comma what?
52.
52. So these are our two. What are these called? Ordered pairs. So even though we are in the given section, it's almost like we did one of the things for the find, isn't it? We have represented this model with ordered pairs, right? So let's go down and do our solution. So now we have all other information doesn't really help us. So I mean, she said it was linear. That's important. That's the whole reason why we're doing all of this stuff that we're doing now, right? Because she said it was linear. And yeah, that's all the information. That's pretty much all the information the problem gave us. Let's go back. So now let's do our solution. So let's start off. We already did the first part, which was ordered pairs. And what were our two ordered pairs? 137 and 250, 52. Right? So we already did our ordered pairs. Let's make a graph. Now, when I say sketch a graph, this is more so what I mean. So on this side, we'll go up by 25. No, that's too small. We're going to have to go up by like 50. So we'll go 50, 100, 150, 200, 250. Usually the ideal scenario is that you go up by the same thing for your inputs and your outputs, but sometimes you can't, just to try to like fit everything on there. So for this one, we'll go up by we'll do the same thing. We'll go up by 50s. So we have 50, 100, 150. All right. So now let's graph the first one. So the first one is 137. So where's 137 going to be? March over to 100.
Move over to 100 and then go up a little bit under 50.
So it's a little more than halfway. So we'll put a point right
Hey,
there.
Professor, can I interrupt really quick?
Go ahead, Bianca.
So while I was online with you all, my son got into the bathroom. He's only one, so can I get off? Because I need to give him a bath.
Yeah, go ahead. He did something nasty. That
He's
sounds.
just messy. He was banging on the door, and I thought he was banging on the door to get in, but he was banging on the door to get out of the bathroom.
Ah.
So, yeah.
All right, go ahead. Have fun.
Okay.
All right. So that's our first. So that's our first point, and then our next point is what?
250. You go up to 52.
So a little above.
50.
What did I just do? All right, and then we can draw a line. I'm trying to draw a very neat line. This is my OCD playing games right here. There we go. Perfect. That's a perfect line. Because the line, of course, it continues off in both directions. So now we've graphed it. We haven't graphed the entire line, but we could theoretically just continue the line out. Just like this, as far as we wanted to continue this line away. Right? We could do that. Continue our line out, and that's a line. That's the line. I mean, there's nothing else to it. We just graphed it. We graphed using those 2 points. And again, how many points do we need to make a line? We only need 2. That's all we need. We just need 2 to make a line. All right? We don't need more than 2 to make a line. So we've done our graph, and now what's the last part that we need to do? A what? Make a what?
Rise and run. Rise over run.
Equation.
An equation. So yes, we will need to do rise over run to make our equation. What's the form our equation is going to be in? We already said it. Y equals mx
plus b.
Now we know it's going to be in that form because we have assumed that it is linear. And because we assume it's linear, that tells us that it's going to be, at least we are assuming it's going to be in this form, right? So as Bianca sells more and more brownies, she might get different points, and it might not be linear when she looks at it. She would assume that it's some other shape. So next time we're going to be talking about like exponential functions, and she might be assuming that. But in this case, we assumed it's linear. So that tells us it's in that form y equals mx plus b. Now to write it in this form, what are the 2 things we need to know? We need to know the slope, and we need to know the y-intercept. Right? This is b, and this is m. So we need to know those 2 things. And once we know those 2 things, then we can rewrite this with the equation of our function. We don't know those 2 things yet. So let's start off by finding the slope, right? That's what we need to find first. And we can find the slope using those 2 points there, because we can do what? Rise over run. Y'all can't probably see that. So how can we do rise over run?
Rise over.
We added 2 points. How can we do rise over run?
We gotta look at the
So there was a
how
way
far
I
over-
give
Is it the m equals? Is it the 100? Oh,
Is it
okay.
32?
Remember this? Y2 minus Y1
Y1.
divided
Over
by...
x1 minus x2. X2 minus x1. I mean.
Yes, exactly. So that's how we do... That's basically rise over run, right? That's the Y value for this point minus the Y value for that point. Or basically what the difference is in the Y's, which is the rise, and then the different divided by the run, which is the differences in the X's. And that's it. Rise over run. So the second point, we'll call this one 2. We'll call this one 1. So do y2 minus y1 divided by x2 minus x1. So what are we going to get when we do this? What is y2? So this is point 2. And this is
52.
15
52.
52
minus 37.
minus 37 divided by
250 minus 100.
and what do we end up with?
Calculator.
It's 15 over 150.
15 over 150, which equals what? What's 15 divided by 150?
Ten.
Not 10.
0.1.
0.1. Y'all doing 150 divided by 15.
It's 0.1.
Yes, it's 0.1. You get a ticket, Shamika. Here you go.
I did what my calculator said.
Oh, you did it on your calculator. That's fine. All right. So 0.1. That's what we get. 0.1. All right. So this 0.1 is our slope. So now we need to find the y-intercept. So what we're going to do is we're going to take the slope. We're going to plug it into there. Right? And then we're going to find the y-intercept because that'll be the only thing we don't know. So we have y equals m. M is 0.1 x plus b. Uh-oh, the two other things that we don't know. What are the two other things we don't know?
Go back to the top of the problem.
X.
The y and the x.
The X and the B.
Well, we don't know b, but that's what we're trying to find now.
Trying to figure out.
Right? But we don't know y and x. But do we have a y and x we can use?
Yeah, it's one of the order pairs.
It's one of the what?
The order pairs.
I can't. You breaking up a little bit.
Can you choose one of the order pairs to put in Y and X?
Yes.
Okay.
Which one should we choose?
It doesn't matter.
37.
130. The 100 and then the 37.
The 137? Yeah, sure. Let's choose that one. So, what are we going to put in for y?
100.
37 equals
37.
37.
So 37 equals what?
0.1
0.1.
100.
times 100 plus B.
There we go. And now there's only one thing we don't know, which is exactly what we wanted. We wanted to just not know one thing. So I want you all to try to solve this. Try to solve this.
Jesus. Okay.
Oh, I remember this part. Hold on.
Is it 27 equals B?
Yeah, I got 27 too.
You got what? 27?
27.
7.
You got B equals 27. So how are we going to do this? First, we're going to do 0.1 times 100. What's 0.1 times 100?
10.
10.
10.
So we have 10 plus B
B.
equals
Equals
37.
37.
37. Now we need to subtract 10 from
Subtract
both
it.
sides. So we do minus 10
10.
minus 10, we get 27 equals 0 plus b, and we get, that 0 can just go away. We get 27 equals b. So yes, 27. So now, what was I gonna say? What was I gonna say? Oh, so that's B. 27 is B. Right? Now we can rewrite the equation. Right? And do y equals, what was M? 0.1 x plus 27. So now I want us to let's examine what this 27 means. What does this 27 mean? If we look up here, right, when we extended that point, didn't it kind of look like it's like crossing in between the 0 and the 50, right? If we look up there, see how it's crossing in between the 0 and the 50? Can somebody try to examine and analyze what does that 27 mean? What was the other thing we called the 27?
The Y-Intercept?
Yeah, but there was another name we called it. What was the other name we called it?
What?
Is
The
it
slope?
Was it the rise? No,
The what? Say it again.
I said the rise. Was the rise?
The slope? What are we talking about?
That was B. What is the other thing we called that? B.
I'm confused.
B.
We called
B
it
was
the
27. What was the other thing we called it? We called it the Y-intercept, but there was something else we called it.
The slope. No. Hold
I'm
on.
thinking the slope too, but I'm confused now.
The intercept.
Is it the rise?
Not the
The
rise.
dependent?
There's one other
The
thing.
rise?
Starts with an S.
Not the slope. No.
The slope?
The slope. It's not the
It's
slope.
not the slope. It's another thing.
Solution?
Starts with an S.
Yeah, I don't know.
Solution? He said it starts
Nope.
with an S.
S-T. I'm going to give it, what's the name to whoever gets it. You can get a virtual ticket to whoever gets it.
God, what is it?
S-T.
Starts
It
with
can't be the
S-T-A.
No.
You said the ST?
S-T-A.
Is it the scatter plot?
Status?
Starting point.
Status?
Starting point. Yes, it's the starting point.
Starting.
I said it.
Who said it?
I said it. I said, hold on.
I feel like I heard two of you. I heard two of you say it.
I said it. It was me.
It was actually.
I said starter, but I didn't say point.
I did. I said it.
You said starting, but you ain't say point?
Yeah, I didn't say point.
Okay, so I'll get ticket too, okay? All right, so yes, it's the starting point. And we look right here, what's it saying our starting point is? Our starting point is 27. So what does that mean? What does that mean? What does that starting point mean for Bianca, who's making the brownies? What does that starting point mean for Bianca?
That
Anybody?
she had 20. She started with 27 or whatever. That's what she had. Or I don't know.
Well, what is the output? What is the output? What did we say the output was in this case?
I think if it was not zero.
What did we say? Let's look at it. What did we say that the output was? Look at our given.
The brownies,
The number of brownies she
Nope,
made.
that wasn't the output. What was the
the
output?
money she spent. The money she spent.
The money she spent. Yes, was that
The
Lisa?
money she spent. Yes. Somebody needs to.
Yeah, I'm putting the Leo on mute.
Was it the amount of money she spent?
Yes, the amount of money she spent. So what that's saying is that basically, when she makes 0 brownies, how much money is she gonna have to spend? You gotta take it off mute, Aaliyah, if you want to say something.
$0.
Nah.
No, she's not gonna have to spend $0. When she makes 0 brownies, how much money does she spend?
$27.
Say it again, Michelle.
$27.
Exactly. When she makes 0 brownies, she has to spend $27. And if you think about what that means, think about what she has to do. Right? Let's try to make it a real scenario. To make it a real scenario, right? Let's say Bianca decides that she's gonna make a brownie business, right? She decides it. She just thinks about it. She hasn't made any brownies yet. Isn't there stuff that she's gonna have to buy just to be able to start the business?
Right.
Yes.
Right?
Yeah,
she might have to buy some pans. She's not gonna have to keep buying pans over and over again. She's gonna have to buy pans. She's gonna have to buy, maybe she has to buy oven mitts and a pan, and she has to buy, I don't know, like a little whisk thing, like a little KitchenAid joint, right? It's gonna be a couple of things that she has to buy before. I'm not talking about the actual brownie mix, because she's buying the brownie mix like that's the cost per brownie. We're talking about what she has to buy just to be able to start the business. That's what we mean when we say starting point. It's what she has to buy just to be able to start the business, right? That's what we're talking about. What she has to buy just to be able to start the business, right? So, I mean, we didn't detail it in this case, but that's what the starting point would represent. Before she even makes money, before she even goes to make brownies, she's gonna have to buy $27 worth of things just to start the business, right? Just to be able to start it, she's gonna have to buy $27 worth of things. So that's her starting point, right? Which kind of, I mean, it kind of makes sense. It kind of actually makes the scenario real. Now, how much is she paying to make one brownie? How much she pay to make one brownie?
Make one?
Yes. Based on what we found here, how much is she paying to make, how much does it cost her to make one brownie? Like, she paid all her startup costs. What does she have to pay to make one brownie?
Is that?
At the 37, I don't know, 37?
No, not the 27. What
Is
is her cost per brownie? That's what we're asking for. Her cost per brownie. What's her cost per brownie?
Oh.
So would you divide that?
No, we don't need to divide, because that's gonna be included if we just divide it. It would include her starting point, right? But look at it, like, so if the Y-intercept is the starting point, right, and like the startup cost. Somebody just said something, but I didn't hear what they said.
No, I'm just thinking of.
So let's look at it. If the Y-intercept is her starting point, let's look at this. This is what we need to look at. This right here. So if we have Y equals 0.1 times X plus 27.
It's not 10?
It's not 10. It's 0.1.
It's 0.1.
Times X, right? Plus 27. 0.1 times X plus 27. So we know what this number is. We know what that is.
It's not the 0.1?
It is the 0.1. That is what she pays per brownie. She pays 0.1, or what? What would 0.1 be in money terms? It'd be what? 10 cents, right?
Mm-hmm.
So she pays 10 cents per brownie, right? She pays $27 of startup cost, and she pays 10 cents per brownie, right? She pays 10 cents per brownie and $27 as a startup cost. So the question is, right? Not the question. I guess the point. We answered the question. This is what she pays per brownie. And if we look at it, it kind of makes sense. And then I'll say what, like, not the question. I meant to say more like the point, like the important thing here, right? For this example, we'll kind of relate this to the real world. If we look here and see how it makes sense. Let's say she decides to make 1,000 brownies, right? So if she decides to make 1,000 brownies, what's she gonna have to do? If she decides to make 1,000 brownies, well, we put the 1,000 into there because that's how many brownies she's making. But realistically, what would she have to do realistically? Realistically, right? She would have to do what? She would have to multiply, like in real world. Ignore the equation for a second. She would have to multiply that 1,000 times her cost per brownie, right? We said her brownies cost 10 cents for each brownie, for her to make it, and then add on all the extra startup cost. So when we do that, that's how we get the total cost for the 1,000 brownies. And if we look here, our equation matches that. We put the 1,000 in here.
In here.
Right? We put the 1,000 right here. What do we multiply it by? We multiply it by the cost per brownie. If she had no starting cost, right, it'd just be like it cost her 10 cents. She makes 1,000 brownies, and you would know what to do. How much is it going to cost her? Well, 10 cents times 1,000. That's easy. But there's a starting cost, so we put the starting cost in there too. That's why we add the 27 in there, right? So we have the cost per brownie plus the startup cost, right? And that's kind of the scenario that you'll have, right? You'll have this scenario for every linear relationship, linear situation, linear model that you create. You'll have this kind of scenario for every linear model that you create. You'll have this kind of scenario. Yeah, so you should always be looking for those two things: the starting point, and then you should be looking for the cost per whatever. And it might not be a cost. It might be the amount per this amount, right? That's what you want to look for next. The cost or the amount or whatever it is per whatever amount. Like another thing that we'll call that, outside of calling it the slope, another thing we'll call it the unit rate, right? So that's another thing you can call the slope. You call the slope the unit rate. So with that, we've done our entire example, right? And we are finished with our examples for today. Now, before I stop the recording, I just want to know if you all have any questions or something you want me to clarify on here.
I have one quick question. This is Kenyatta.
Go ahead.
My question is, can you scroll down just a little bit?
Scroll
just
down.
A tad bit.
Down?
I'm sorry, up. Scroll up.
Okay. Scroll
so
up.
Don't you know when we get to the point where we say, when we get to the order pairs and we have to put in our we have to choose an ordered pair.
Your question is, does it matter which one we choose?
Yes,
Nope.
I put that as a question.
You can choose any point. What I usually recommend is choose the one that looks like it has easier numbers. So in this case, working with 100 is a whole lot easier than working with 250. So that's why the 100 kind of, in my head, makes more sense. But it doesn't matter. If you put the 250 and the 52 in there, you're going to get the same starting point. Right?
Yeah, because I did that with one of the examples that you had, and I used one, then I used the other, and I was like, oh, okay, same thing. Thank you.
Okay. Aaliyah, you asked for practice problems. Yep, I'll send you all some practice problems. I have a couple. I'm going to send them out.
Yes.
Yeah, so I'll send the practice problems. Anybody else have questions about what we have up here? Other questions about what we have up here?
And I think you should give somebody a ticket for saying to do all three. For the fine.
Who was
I'm just
that?
saying.
Was
that
that
was really
Ashley
good.
or Aaliyah that said do
I think
all
it was
three?
Ashley.
It was
I'm not
Ashley?
sure, but that was great. Thank you.
What did I say?
You said do all three.
I did.
So I'll give you a ticket for saying do all three.
Okay. At first I was like, but now I'm like, yay.
All right, so let me stop this recording really quickly.